Okay, so we'll do this one on line paper. I don't do this too often, but every once in a while I like to do a good old-fashioned line paper note just to mix it up. So we said atoms with partial shells are not stable. What the heck was that? Was it? Oh, anyway. There we go. All right. So we said that atoms with partial outer shells are not stable. So one way to become stable kind of charming. So one way to become stable is to give or take electrons. That's the previous note. And we'll say here C1.2, right? You can always remind yourself what note you'll find that in. But today, we'll say another way is to share electrons. What's it mean to share something? I mean, it's kind of a stupid question. I guess we all know what that means. Presumably you learned this in like kindergarten. Anyone here an only child and thus never had to learn how to share? You can admit it now. One of my best friends was an only child. The guy didn't know how to share. No, but seriously, if you're sharing something, like, describe that to me. What's it mean? Yeah. Yeah, that's right. So, and usually, do you both have it at the same time? Usually not, right? Usually it means that spends some time with one of you and some time the other. So this is called forming a covalent bond. And whenever you see co as a prefix, cooperate, co-parent, cohabitate, collaborate. That's a good one, right? Collaborate. Collaborate's actually a good one because what's that mean? What two words are in there? Co and labor. Labor means to do what? To work. But to collaborate means to work together. If you talk about co-parenting, parenting means to raise a child. Co-parenting means to raise a child together. Good. Cooperate. Operating means to do something, and co means together, so it means to do something together. See that? Yeah.
Is it just a weird looking word, or is collaborate spelled with two L's?
Is it two L's? I don't think so.
It looks weird with one.
I think it's just one. You look it up. It shouldn't be, but then English is weird, right? Anyway, co means together, and valence just means. Does it? Wow, guys, I apologize.
I thought it looked weird because it uses the American spelling of labor.
Yeah, that's true too. So, covalent means that they have the outer shell of electrons together. Some of their outer electrons they share. Covalent. That's one word, by the way, and the way I've written it there, it kind of looks like it's two words, so I'm going to rewrite that. Thank you for correcting my spelling, by the way. I'm not a great... That's really nice. I like that. I feel like I need I should have like a number. I need like a soundboard, like the air horn and like that, and like clapping, like applause, laughter. Every time I say something funny and nobody laughs, I can just press the soundboard and get like uproarious laughter. I might do that. Yeah. Now, the only thing about this is sharing, your parents probably taught you to share with people who don't have anything, right? Like your parents probably taught you that, if you have a toy and there's another kid who doesn't have a toy, you should share with them. This is not the way atoms operate. Sharing is always equal, which means atoms will only share if they can share equally. In other words, they will only share an electron if they can both share an electron. They'll only share 2 electrons if they can both share 2 electrons. Does that make sense? Which means that a rich atom is never going to share with a poor atom. Does that make sense? So, this sharing... Oh, thank you. Is always equal. I.e., 1 electron from each atom. So only the nonmetals can share. And the nonmetals, if you're trying to remember, on the periodic table, make up a very small minority. When we talk about the table kind of looking like this, we are only talking about this little tiny segment here. Basically, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, sulfur, phosphorus, and hydrogen gets to play, even though hydrogen lives way over here, because hydrogen, even though it only has 1 electron, actually almost has a full shell, because hydrogen and helium are the only 2 that only have how many electrons to have a full shell? Just 2, right? So again, that really is the list of the ones that can do this. Hydrogen, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, iodine. So let's look at an example. I'll give you a minute to draw that. Sorry, I'm not trying to rush you. On the back half of this. How many of you did you all use a Bunsen burner last year? Everyone on the Bunsen burners? Yes? Little metal thing, fire on top, you burn things in it. Interesting. What about you guys? Did you use a Bunsen burner last year? Okay, well, we'll get there. Because I'm hoping to use them tomorrow. So maybe at the back half of class today, we'll make sure you remember how. Okay, we'll look at an example of water. What is the chemical formula for water? This is like the chemical formula even kids know. Yes, correct. H2O, which means it's made of 2 hydrogens and 1 oxygen. Cool. So if we look at this, we have a hydrogen, and we have an oxygen, and then we have another hydrogen. Now, looking at the periodic table, oh, Toby, get in there. Hydrogen, how many electrons in its outer shell? Which also happens to be just how many electrons it has total. Do you want a ruler, Toby? Yeah, let's do this. This is good. We're going to be a tag team. This is going to be great. Also, if you need to hit anyone, great. Hypothetically, Heimple, you just do what you got to do. How many electrons does hydrogen have in its outer shell? Yeah, 1. Good. So this hydrogen only has 1 electron, and this hydrogen only has 1 electron, so it's not stable. What about oxygen? How many electrons in its outer shell? 6. Yeah, and how'd you do that? You're totally right. How do you do that? How do you know 6? Yes, my friend. Yeah. Okay, yeah, that'll get you there, absolutely. Why does that work? The way the periodic table is set up is that every time we start a new row, we're starting a new shell. So oxygen's in the second row, so it's got a second shell. In that second shell, lithium would have 1 electron, beryllium would have 2, boron would have 3, carbon would have 4, nitrogen would have 5, and oxygen would have 6. So wherever you are on the periodic table, if you just count over from the left, which you're totally right, it so happens that if you just take the number 1 off the top, that'll work. But the reason for that is that on the periodic table, every new row is actually a new shell. When I was a kid, they had different names for the groups, and that was actually called Group 6B, which was annoying. But anyway, same idea. So oxygen has 6 electrons. How do we normally draw them? Would I draw them like this? No, how do we normally draw them? Usually we draw above, below, left and right. That gets me to 4. I need to get to 6, so I'll do 1 more up here, 1 more down there. It doesn't make a difference where you put the extra 2, but in this case, we want to see here. Now, if these were going to form an ionic bond, hydrogen could just give its electron to oxygen. But when the rich atoms, when the atoms that have almost full shells interact with each other, they don't give away their electrons. Because you can imagine it like this. Does anyone collect anything? Comic books, baseball cards, bottle caps. Yeah, what do you collect? Oh, I love that. That's a bad example for what I'm going to talk about because I don't really know when you'd be out of, like, when you could almost have a full collection because there's a lot of rocks in the world, right? But, like, let's say, or has anyone ever played, like, the Monopoly game at McDonald's? You know that thing? If you had, like, an almost full board and you're missing just one thing, are you going to give any of yours away? Of course not, right? On the other hand, if you just had one, if I don't go to McDonald's often, but I went through and got a coffee and I have one little thing, am I happy to give that away? Yeah, because I'm not going to get to a full set, right? So everything on the left side of the periodic table is happy to give things away. Everything on the right will take things, but it won't give away, but they will share. Does that make sense? If you have an almost full shell, you're not going to give your electrons away, but you will share. And so what happens is hydrogen and oxygen can share these electrons. They're shared. And the other way we can say that is that they are covalent, which means that that blue electron now doesn't just spin around hydrogen. It's actually going to spin around hydrogen and around oxygen. And likewise, that yellow one isn't just going to spin around oxygen anymore. It's going to spin around hydrogen and oxygen. And it will also share these ones. This is what we call a covalent bond. And in fact, how we usually draw that and you've probably seen chemical drawings like this before, we will usually just draw shared electrons as a line. I would still have to draw the electrons that aren't shared, like this. So a single line is a shared pair of electrons. And whenever nonmetals form bonds with each other, they're covalent. Make sure you got that. If I'm ever going too fast, by the way, and you need more time to write, all you need to do is say, hey, Orlando, slow down. So please don't be shy to do that. I get excited about chemistry, just like you guys. I can see how excited you are. And so sometimes I have a habit of going too fast. I know you all woke up today and you're like, we're going to talk about covalent bonds today. That's so exciting. But you know what? That is exciting for me. I get very excited. Don't give me that look. I don't know what to tell you. I mean, the truth be told, like this part of it's dry, right? Like where you're just learning like this on paper. But Once you actually get working with it, it's tremendously interesting. So you got to do a bit of this kind of dry paperwork before you can like jump in the lab and get doing stuff. But this is actually, I think, really interesting. Now, when we do this, it leads us to the idea of carrying capacity. If you notice here, if we look at water again. Sorry, what's that? You guys just keep on correcting my spelling. But I don't think that was a spelling error so much as, what's the equivalent of a typo when you're handwriting? Fair enough. I guess that's the right answer. But not a spelling error. Like it's like a writing error. Do you see how that line ever so slightly tilts up? Can you see that? Now I would ask you, why in the world is that an option even? Like, why would it ever be like, you know what this guy probably wants? He probably wants a line that is almost but not quite straight. Right? Like, I don't understand. So each atom will share as many electrons as it takes to get a full shell. Are you comfortable if I write E negative for electron? I should write the word electron. That's a bad habit to throw that at you without explaining it first. Let's take a minute with that. So if we look at water for an example, right, like we just did, with water, we noted that oxygen started off with 2 electron pairs that were already full, right? So this here is the lone pair of electrons. There's no bond there, they're just already there. Does that make sense? And the word we use for that is lone pair. But this is a shared pair of electrons. And the other word we use for that is a covalent bond, right? Because the fact that the electrons have to orbit oxygen and hydrogen will make oxygen and hydrogen stick together. So now, with that in mind, let's count. How many bonds is oxygen making? Oxygen's here. How many bonds is it making? Yeah, very good. It's making a bond to this hydrogen and a bond to that hydrogen. So oxygen makes 2 bonds. And on the other hand, hydrogen makes how many? Yeah. And if you think about looking at the periodic table, that makes sense. How many electrons does hydrogen need to gain to get a full shell? Just 1. So it makes 1 bond. Look at oxygen. How many electrons would oxygen need to get a full shell? 2. So how many bonds does it make? 2. Boy, you guys are a tough crowd today. I feel like I need to get Kelford in here and have him rap this whole lesson or something. Or do I need to sing it? Should I rehearse this as a country song? Get some twang in my voice.
I mean, you already have
oxygen. So oxygen makes 2 bonds, and I could just play a little guitar. Have someone play the fiddle behind me. Should play the fiddle? Anyone play the fiddle? Now let's get on that. Sorry? No? I play the violin, but very poorly. I would not want to play it in front of people. I take violin lessons, and I'm still abysmal. I've been doing it for 6 years now. And I somehow seem to be getting worse. It's depressing. Anyway, okay, so generally speaking, we can actually look at the periodic table here. And if you look, in group 14, we have carbon and we have silicon. And then next to that, and they need how many electrons to get a full shell? Carbon would need 1, 2, 3, 4 more. Does that make sense? One more would make it have 5 electrons, 2 more 6, 3 more 7, and by the time it has 4 more, it would have 8 in a full shell. So these will make 4 bonds. What about oxygen and sulfur? Oxygen, oh, sorry, I skipped. What about nitrogen and phosphorus? They have 5 electrons right now. To have a full shell, they need 8. So they would have to make 1, 2, 3 bonds. So nitrogen and phosphorus will tend to make 3 bonds. What about oxygen and sulfur? They're obviously going to make 2 bonds because they just need 2 electrons to have an outer shell. So oxygen and sulfur. And then making 1 bond, obviously we have fluorine, chlorine, bromine, iodine if it's involved. But what else only needs 1 electron to make a full shell? What's the other thing on the periodic table that only needs 1 more electron to have a full shell? Hydrogen. So we include that in our little club here of things that only need to make 1 bond. Hydrogen, fluorine, chlorine, bromine, and iodine. And the nonmetals can be covalently bound together just like Lego. Like Lego, the only thing limiting how many ways you can put them together is how many you have. Does that make sense? You can build ludicrously complicated stuff with this. I always use the example, inside your cells, and you have thousands of these inside every one of your cells, you have a machine that spins around like a top and makes other molecules, like a little factory. It's called ATP synthase. And your cell is just full of them. But it's like this little machine that literally mechanically spins and puts molecules together. And that's just 1 molecule that's stuck together, big and covalently bounded like this. So you can make big, complicated stuff. All of the big, complicated molecules of life and the only rule is that they need to make the right number of bonds. So if I work with carbon, how many bonds is it going to have to make? Boy, that's a tough crowd. Carbon always going to make how many bonds? 4, good. So let's look at carbon dioxide, CO2. We said carbon makes 4 bonds. How many bonds does each oxygen make? Yeah, very good. So how does this work? If I have carbon here, oxygen there, and oxygen there, carbon wants to make 4 bonds, oxygen each wants to make 2. You can make more than 1 bond between them. Carbon can make 2 bonds with this oxygen, and it can make 2 more with that oxygen. How many bonds is carbon making now? Carbon's making 1, 2, 3, 4. Good. And how many bonds is this oxygen making? 2. And this one? 2. So that works. That's the structure there. We call this a double bond. A double bond. It's a good name. That's what happens when you bond two things together. Sometimes we need even more than a double bond. Nitrogen gas is N2. In other words, when you find nitrogen out in nature, because nitrogen atoms aren't stable, it forms something called nitrogen gas, where one nitrogen atom will stick to a second nitrogen atom. Does that make sense? But we know how many bonds does nitrogen want to make? Very good. So we have this nitrogen here. We have that nitrogen there. How many bonds do they want to make? 3. So 1, 2, 3. What do you suppose we call that? Yeah, very good. And if you wanted to draw it with the electrons themselves, you could actually draw the nitrogens. How many electrons do they have? 1, 2, 3, 4, 5. So you could draw it 1, 2, 3, 4, 5. And over here, 1, 2, 3, 4, 5. And how do they form bonds? Well, it's going to share these electrons with each other, and it's going to share those electrons with each other, and it's going to share those electrons with each other. There is no quadruple bond. The geometry doesn't work. You'll learn in grade 12 kind of why it can't happen. But triple is the most number of bonds two things can make with each other. So carbon makes 4 bonds, but it can only make 3 bonds with a single other atom. So between any 2 atoms, triple is the limit. Okay, let's just have you practice and see if you can draw a few things, what they would look like. That's the wrong order for that. See if you can figure these out, and you can draw it either way. If you find it helpful to draw the electrons and then the sharing, that's cool, but usually we just draw the bonds. Do you want to try the first one together? So you got this. I'd just say, what I would quickly check is how many bonds does carbon make? Each C makes how many bonds? Good. Right? And if we want to remember that, it's because it's 4 away from having a full shell. Each H makes how many bonds? That's right? It is 1, yeah. Because again, it only needs 1 more electron to have a full shell. So that one is actually pretty easy. In fact, all these are fairly easy. But give it a shot, see what you come up with. Joby and I are here to help if you need. We'll give you 3 minutes. Yeah. Yep, beautiful. So the H can't connect to anything else. Yep. Now carbon has to make how many more bonds? So that's to make a total of 4 bonds. So yeah, so that'll work, and you can kind of draw them like that. And that's totally fine. How we usually draw it is just we'll show carbon's bonds like this, and so then you can draw an H there, and there, and there. Does that make sense? Those are both right. This is just a little easier to see. Does that make sense? Cool. So that's correct. There's nothing wrong with that. Well done. Yes, sir. In the middle. Nitrogen. So how many bonds does nitrogen want to make to get to a full shell? Yeah, very good. So it's going to make 3 connections. And then hydrogen, how many connections can it make? We already said. And what about fluorine? How many connections can it make? 1. Good. So there's actually only one way to put that together. We'll eventually get to things where you can put it together different ways. I stuck with easy ones to start.
That gets crazy.
Very crazy. Like wild. Out of control. Yes. Yes, ma'am. Right? No problem. So drop carbon. And what I would usually actually do is, how many bonds does it want to make? So just draw the bonds. And just draw a line in each direction, up, down, left, right. Cool. Now, hydrogen all wants to make 1 bond. So this is actually perfect. How many of them do you have? And they all just want to make 1 bond. So where could they go? 1 go there. Great. And it's making 1 bond. It's happy. Where could the next one go? Yeah. Beautiful. Beautiful. Nice. And for this, that's actually the only way you can put it together. Well, I'll give you some where you could put it together 100 different ways, and any one would be fine. But for this one, I don't think that because hydrogen can only make 1 bond, that's the only way to do it. Does that make sense? Cool. Try the next one, which I think is NH3 or N2HF, NH2F. Yeah. Let's check. Was I supposed to give that to you a week ago? Maybe. Well, I don't. Oh, I did. Yeah. I saw. Is that your middle name?
Yeah.
That's the first name one, so it's going to be easy.
Yeah. I mean, it's not good, but I mean, you can see what subjects I like.
2 of them are excellent, and then 2 of them are really rough. That is really funny.
At least I didn't get like 51.
No, you're fine. You're fine. Listen. No, but what it tells me is you definitely know what you like and what you don't, right? That's really funny. But I mean, that was brutal. That's a brutal.
Oh, yeah. I don't know how I got that in manufacturing. Like, I thought I did so good and I got it back. I asked him, I was like, am I doing good? He's like, no, you're doing great. And then I get that. I was like, what? And look at the comment. He's saying I did great.
May I read it?
Yeah.
Hers machining skill. I think that's supposed to be her machining skills. Yeah. That's okay. Have improved. And he's able to work with an engine lathe and overhead milling machine with limited supervision. Getting some kind of transgendery things happening here, but that's okay. Autumn is encouraged to take more technology courses and join an SHSM. You might actually want to ask about that. That could be like a typo.
I don't know, because I didn't do good on the assignments. I handed in stuff, but I didn't like on the
were you getting
on
60s?
I was 70s and 60s.
But that's in the 50s.
I know.
And then the comments really positive.
I know.
Do you see what I'm saying?
I know.
You might want to actually ask them that and just be like, and also like, why would like, because for example, if somebody got like in the 50s in my class, I wouldn't be like, take more science, you know?
I'm not going to take any more tech. That was just like kind of a filler.
But it's so much fun. Did you learn to weld? Is that the one where you weld? Is that on the
we
mills
did
and the
grade
lathe and stuff?
Yeah, we
Well,
just.
then I don't know.
Well, my dad welds, so I could just like talk to my dad. And he could just
Still, you should actually ask about that because honestly, that mark doesn't match the comment, and I mean the comment also has issues. Yeah, you might just want to ask, you know, or not. Like I don't know if you care. Like depending on what you do, nobody may ever look at that, right?
Yeah, so, I don't think I want to do science stuff. So.
Well, then yeah, I think you're probably fine. But even just if for your own personal ego,
I
you know.
passed the literacy.
Oh, did you?
Yeah. I don't know where it shows what I got.
Well, congratulations. That's exciting. Nice enough.
Oh, yeah.
Oh, you did great. Wait, the spare.
37 out of 30. Does that mean I got them all?
That's
Right?
attempted.
Oh.
I won't tell them about it so you can make it.
Wait, what is it out of? 400?
I think so. You know what that
Yeah.
is? Yeah. You did well.
And you need it
Yeah, you killed.
37 out of 400.
No, I got
37 out of 400, not a
I
good
don't-
score. It's like a tech score.
What did you get?
What did you get?
Yeah.
It's 300 to pass. And then,
Is it 300 to pass?
yeah, 400 to 500.
I got one.
Cool. What'd you get? Oh, there you go. Now, he's got no proof here. I mean, you can just make him that up. But I gotta say, the look, I believe him. Listen, that's a good score. You should be happy with that.
I'm supposed to get more than
Did you say you're supposed to get more than him? I don't know how I feel about that.
Look at my lates in trushes. Oh goodness.
Man, was that after lunch?
No, it was fourth, but mine is like if I'm on the same minute as the bell, I don't think I'm late.
Of course you're late. Of course you're late. No, what kind of question is that? Okay, listen. No, let's use an analogy. Okay, let's say that you're flying a plane. Right? Let's picture this. Here we are. No, okay, so we're flying a plane. Now, do you want the pilot who says, I think if I pull up exactly as we're hitting the mountain, that I'm on time? Is that what you want? That's the pilot you want?
Am I flying a plane?
Metaphorically, yes. No, but that's the point, right? In other words, on time means that, like, when the bell rings, you're working. I would make the argument that if your book isn't open and your pencil in your hand, you're not on time, right? Like, that's when the bell rings, you're supposed to be working. Now, some teachers may be lax about that, but a teacher who chooses not to be, I'm not, for example. Now, luckily, I always forget to do my attendance, so if you're late in my class, you got a few minutes grace. But in terms of what do I consider late, you don't want to be that employee, let me tell you. I spent more years managing restaurants than I've spent teaching. And you know what kind of employee you hate with an unbridled passion? The one who's always skirting the line of being just on time. Because you're sitting there going like, are they going to be here? Are they going to be here? Especially, did you have absences? How many absences?
Like barely any.
But some. How many? In that one?
Oh, in that one, I have 2.
Okay, so not many, but still some. So now, if I'm your boss, I'm thinking, are they showing up? Are they sick? And they didn't reach out. See what I'm saying? You don't want that employee. You like the employee who's 5 minutes early. That's who gets the raises. That's who gets the bonuses. That's the reality.
And it doesn't help that I had math, so it was like right there.
And Trush, I happen to know, he's a gym teacher, so I bet he said something to the equivalent of, if you're not early, you're late.
I think so.
Yeah, that sounds like Trush. And he was probably like straightening up his desk so it was perfectly organized while he said it. Trush makes me feel so self-conscious. His room is so neat, and his stuff is always so like,
Our class,
just so precise. And then my room is so messy, and I'm so embarrassed by it.
Doesn't stink. That one's stunk.
Well, that's probably not Trush's doing.
I know.
Anyway. Okay, get out of here. I got to teach some chemistry. Get out of here. All right. So we said carbon wants to make 4 bonds. And so the way I would draw this is just draw carbon. And because it's making the most bonds, it's almost certainly going to be in the middle. So just draw it and put it in the middle. And now hydrogen wants to make how many bonds? Just 1. So I could put 1 here. But I need how many of them? 4. So I could put 1 here. And I can put another one here. And I can put another one there. And this would be CH4, which we're going to learn the naming in about 2 seconds. But we would call this carbon. Does anyone know? I don't know why you would possibly know this, but just maybe you've taken this before and maybe you've jumped ahead. Does anyone know the Latin prefix for 4? There's 2. One that you're probably really used to, which annoyingly isn't the one we use here. What do we call like a 4-wheeler or something like that? Quad, good. But that's not the one we use here, annoyingly. But you might know this from a game where they arrange 4 blocks and all the ways that they can be arranged to make shapes. What do we call the game where there's 4 blocks arranged all these different ways? Tetris. Because the prefix for 4 is tetra. And again, we're going to learn this, so don't worry if you didn't know this, but this would be carbon tetrahydride. And again, we're going to learn naming. Don't stress about it. But 1 carbon, 4 hydrogens. Sorry, what's that? Toby, stop wasting my time. What's up?
Hi. It's Toby's wasting your time. It's just tracking their attendance.
Oh, beautiful. Thank you.
It's just the fact that you date that they weren't practicing.
Yes.
Okay.
Yeah.
So, yeah, if you just
Perfect.
check mark that the days are there. And
Sounds great.
They'll come in every once in a while and grab their sheets.
Beautiful. Yeah, sounds great.
Get Toby's feedback grade.
Yeah, Toby's wonderful. Why don't we give this a home next to the computer back there? Why don't we give it a home on the computer back there? Yeah, on the cube. That'll do well. It's not what Trush would do. Trush would have like a space. How many bonds does nitrogen want to make? How many? How many bonds, nitrogen, up there? It has, 1, 2, 3, 4, 5 electrons. It needs to get to 8, so it's going to make 1, 2, 3 bonds. And again, you don't need to have that memorized. I wouldn't memorize it. Just look at the periodic table. It's up there. Hydrogen, to get to a full shell, only needs one more. And likewise, fluorine. These all make one bond each. So, again, this one's pretty simple. What's going to go in the middle? Nitrogen. How many bonds does it make? 3. And so you could just draw them like this. Down here, not that it matters, but we'd have its electrons that aren't shared. And then what's going to live here? Well, 2 of them will be hydrogens. And the hydrogen's happy because it only needs to make one bond to have a full shell. Up here could be hydrogen, and it's going to be happy because it only needs to make one bond to have a full shell. And over here we would have fluorine, and it only needs to make one bond to have a full shell because it started off with 7. So it's got its 6 electrons that it still just has by itself, and now the shared pair. How's that feel? Not too bad? This would be called, and we'll get to the naming again later, but this would be called nitrogen dihydrogen, di meaning 2. And then, what's the prefix for 1? Again, there's 2 of them. Uno's 1. Absolutely, it's not the one we use here, but the game Uno, unicycle, things like that. And the other one? Mono. Good. Like a monocle or a monotone. A unicle. There you go. And monofluoride. Nitrogen dihydrogen monofluoride. Not a very exciting name, but there it is. And how would we draw this? How many bonds does hydrogen want to make? 1 bond. Good. How many bonds does carbon want to make? 4. Great. And nitrogen? 3. So, if we draw carbon here, hydrogen here, how many bonds does hydrogen want to make? 1. Now here I could draw it like this, but there's not 3 more things to connect to. There's only 1. What's the other thing to connect to? But the good news is, how many bonds does it want to make? 3. So we can make a triple bond like that. And this would be called hydrogen monocarbon mononitride. Hydrogen monocarbon mononitride. Now, the thing to know about this is, don't draw this. I mean, or do if you want, but I wouldn't draw this. But this can get huge really quickly because this carbon can connect to 4 things. I could put another carbon here which wants to connect to 4 things, and another carbon here that wants to connect to 4 things, and another one there. And if I wanted to, I could put a carbon up here which wants to connect to 4 of the things. And maybe I put some hydrogens there. Here I put a nitrogen that wants to connect to 2 more things. And then carbons that want to connect to 4 things. And do you see how we could just keep going? Now, in this course, we're not going to do that. We're not going to get building big and crazy things. But the thing to understand is that you could just keep building these as long as you want to keep building them. You can make truly massive things. Your DNA in your cells are just 43 individual molecules. But if you stretched it out, it's like over a meter tall. It's trillions of atoms. No, it's not trillions. It's billions, though. It's billions of atoms put together, all in a single molecule. Just they keep building it. Yeah. Yeah, we're going to get the model kit out maybe today, probably tomorrow, and build some stuff. Did you use the little rubber model kits, like the little plastic ones with the rubber bonds? Yeah, so we're going to use that again. Exactly right. So this kind of bonding can be used to make just about anything. Naming is easy. We use prefixes to indicate how many of each atom is present. What's the prefix for 1? We just said it.
Oh, for 1, mono.
Yeah, 2. This is another one where there's 2. Sometimes they use bi, sometimes they use di. In this case, we use di. 3, you'll know. Yep, tri. Very good. So like triple, like triangle. Yep. 4, we already said. It's the way less common one. It's not quad, which you're used to. It's tetra. Yeah. 5, you'll be familiar with. What do we call a 5-sided figure? Yeah, very good. Pentagon. And probably from the gons, you'll be used to these now. A 6-sided figure is a hexagon. Good. So hexa. 7 you might not know. We don't use 7 as often. Yeah, you're almost exactly right. In French, it's sept. In Latin, which is what this comes from, it's hept. So it's hepta. Very good. 8. Yep. Octa. Yep. Exactly right. Octopus, octagon, octane. Okay. 9. Anyone have an Italian grandmother? Nona. And these keep going, but we'll stop at 10. 10's easy. 10 is deca. Very good.
Last year before you count, somebody made like Murray.
Yeah, and you can look it up. Those prefixes that go up like all the way to 100, we're not going to learn them because they're not going to come up very often. 11 is undeca. 12 is dodeca. 13 is trideca. You get the idea. But anyway, okay. So this is quote-unquote homework, though you will almost certainly get done before you leave this period, which is great. That's what I want. I want you to try and draw and name the following. That's a CL. Sorry, that's messy. CL2. If you need more paper, where is it? Oh, it's right here. There you go. Something else? Oh, sorry. I forgot to say the important part here. So now the name itself, sorry, I did all the prefixes, and then the name itself is, you work from left to right on the periodic table. So if you had hydrogen, nitrogen, and oxygen, you'd do hydrogen, then nitrogen, then oxygen. If you had hydrogen, carbon, and chlorine, you'd do hydrogen, carbon, and chlorine. Sometimes they'll throw hydrogen at the end, and that's okay. Just do it in the order you see here. But generally speaking, left, right on the periodic table, but H is often last instead. And that's okay. Honestly, I wouldn't call you wrong either way. If you put H at the front, I'll mark you right. If you put H at the end, I'll mark you right. Either way is fine. Don't worry about it. And then we do the prefix plus name. But the last one, change the ending to "ide." Because the IDE, "ide" ending, tells us it's a compound. So, let's try one. Let's try C2H6. That would be, well, we start with carbon, then hydrogen. We do the prefix plus the name. So, carbon is carbon 2. So, how many carbons? 2. So, the prefix would be di. So, this would be dicarbon. And then there's 6 hydrogens, so it would be hexa, hydrogen, but then we drop the ogen and we change it to hydride. You might mix up where to take it off. Like if you'd called it hydronide or something, hydrogide or something. Don't stress. You'll get used to where because it drops a little different on different things. Like phosphorus, they drop the whole urus and it just becomes phosphide. But then like something like chlorine becomes chloride. You'll get a feel for it. And if you make a mistake, don't worry about it. You'll learn. Let's try one more together. If we had NH3, that would be, and this is the one rule, the other rule we're going to know, we call this nitrogen. And then what's the prefix for 3? Trihydride. And then here's the one rule. We don't put mono on the first. If mono would appear on the first, it's not wrong. If you called this mononitrogen trihydride, that's not a wrong answer. But they usually leave mono off the first one and then put it on everything else. Again, if you put it there, I'm not going to mark you wrong. I'm just going to tell you, hey, we drop it on the first one. But we usually don't write mono just for the first element. Did I say wrote? Oh gosh, that's embarrassing. And that's it. So that will come with a bit of practice. You're going to get lots of practice. Tomorrow we're just going to get the model kits out and build some stuff and name some stuff and maybe get down into the lab if time permits. For today, we're going to draw and name the following. CH2 there. We'll do NH2F.
My favorite compound.
Right? Sorry. Don't know where my mind went there. I got this. Sorry? It would be tetra. Wait, now I'm having a moment. Yeah, it is. Thanks. Not that it matters. I'm not asking you to draw it, but I should still give you names for things that are real. Yes. Cool. All right. So that's your homework, such as it is. You've got the time that's left to do it. If you have any questions with this, let me know, and then tomorrow we'll reinforce.